Hello and welcome to today's lesson on perfect black bodies. We will begin today's lesson by learning what a perfect black body is, an idealized object that absorbs all the radiation incident on it, regardless of wavelength or angle. Next, we will discuss how perfect black bodies are also perfect emitters and how, when heated, they emit radiation very efficiently across a wide spectrum. Finally, we will explore examples of objects that approximate perfect black bodies. So far, we have explored how objects emit infrared radiation and how the emission varies based on their temperature and material properties. Building on this understanding, we can now delve into the concept of perfect black bodies. This will enhance our understanding of how idealized objects interact with radiation, providing deeper insights into real-world phenomena and advancing our grasp of fundamental physics principles. Let's get started! Let's begin by defining a perfect black body. A perfect black body is an idealized theoretical object that absorbs all incoming radiation, regardless of the radiation's wavelength or angle. Imagine it as a perfectly matte surface with no reflection or transmission whatsoever. Because it does not reflect any light, a perfect black body appears completely black. The efficiency of emission by a perfect black body makes it a unique and useful theoretical model in physics. When you heat a perfect black body, it emits very predictable and consistent radiation. The amount and wavelength of the emitted radiation depend on the body's temperature. For example, when you look at the spectrum of the radiation emitted by a hot object, it follows a curve known as the black body spectrum. This spectrum shows that as the temperature of the black body increases, the peak of the emitted radiation shifts to shorter wavelengths. This is why hot objects, like stars, can emit visible light that we can see. According to Planck's law, the intensity and distribution of electromagnetic radiation emitted by a perfect black body are solely dependent on its temperature. This means you can determine the temperature of an object by examining the spectrum of the radiation it emits, which is extremely useful in astrophysics for studying stars and other celestial bodies. In reality, a perfect black body does not exist, but some objects come close to approximating its properties. Stars, such as the Sun, are often modeled as perfect black bodies because they emit a wide spectrum of radiation very efficiently due to their high temperatures. The Sun's radiation closely matches the black body curve, corresponding to its surface temperature of approximately 5,500 degrees Celsius. Another example is certain laboratory materials, such as those coated with lamp black, a type of soot that absorbs most of the radiation that strikes it, making it a good practical approximation of a perfect black body. Scientists use such materials in experiments to study the principles of black body radiation. In today's lesson, we delved into the concept of perfect black bodies, theoretical objects that absorb all incident radiation and appear completely black due to the lack of reflection and transmission. We discussed their unique characteristic of emitting radiation very efficiently when heated, referred to as black body radiation. This emission follows a predictable spectrum that shifts based on temperature, which is crucial in understanding objects like stars. Although perfect black bodies do not exist in reality, approximate examples such as the Sun and materials coated with lamp black demonstrate similar properties. By studying these principles, we gained a deeper understanding of how objects interact with infrared radiation, enhancing our knowledge of thermal physics and its practical applications in fields like astronomy and material science. Watch the rest of the GCSE physics course at Sophos Education.